You ever see something move in a way that just doesn't quite add up? Well, it turns out that how you see motion depends entirely on where you're watching from. So let's dive into this totally fascinating and honestly kind of weird concept, relative motion.
All right, we're going to kick things off with a little puzzle. This is something you might have even tried yourself, and it all starts in a moving car, with an apple.
So get this, you're driving down the highway, you finish your apple, and you toss the core out the window. For a split second, it zips backward, right? But then, it almost looks like it's trying to keep up with your car. So what's the deal? Did you just break physics? Nope, not even close. Here's the key thing you gotta remember. Before you even threw it, that apple was already moving forward at the exact same speed as you and your car. When you toss it out the side, you're not really throwing it backward relative to the road, you're just slowing down its forward momentum. So from a bird's eye view, it's actually still moving forward, just not as fast as you are anymore.
The real trick, the illusion, it all happens right inside your own head. See, at first, your brain is using the car as its point of comparison, its frame of reference. Compared to the car, yeah, the apple is moving backward. But the second it's out in the world, your brain instinctively switches its reference frame to the ground. And suddenly, you see what's really happening. The apple is moving forward, but you're just moving forward faster.
That whole idea of a frame of reference, that's the secret sauce to all of this. So let's really unpack that and see how two people can look at the very same thing and see something completely different.
Okay, this is the classic example, and it's perfect. Imagine you're on a train, moving at a nice steady speed. You toss a ball straight up in the air. To you, it just goes up and it comes straight back down into your hand. Easy. But what about someone standing on the ground watching your train go by? To them, that ball isn't just going up and down, it's also moving forward with the train. So they see the ball trace this beautiful, long, curved path, a parabola. So who's right, you on the train or the person on the ground? Well, the amazing answer is you both are.
So, if motion can look totally different depending on your point of view, how on earth do we measure anything consistently? How do physicists agree on how fast something is going? Well, they've got a really smart system for that.
They used what's called an inertial reference frame. Now, that sounds super technical, I know, but it's actually a pretty simple idea. It's just a fancy way of saying the point of view we all agree to pretend is perfectly still. It could be the ground. It could be the train. By picking one, we get a nice, stable baseline we can use to measure everything else.
And from there, we can actually calculate this stuff with some pretty simple math. The velocity of object B, from the perspective of object A, we call that VAB, is just the velocity of B minus the velocity of A. The only trick is making sure both those speeds are measured from the same reference frame, like the ground. Let me show you how it works.
Let's go back to our trains. Say train A is chugging along at 50 miles per hour, and on the next track, train B is doing 60. Now, if you're standing on the ground, they both look like they're flying by. But if you're sitting on train A, what do you see? You're already doing 50, so train B doesn't look like it's going 60. To you, it just looks like it's slowly pulling away at, you guessed it, 10 miles per hour. That is relative velocity.
Now, all this talk about reference frames and relative speeds might sound like some 21st century physics, but the basic idea was actually hammered out almost 400 years ago by one of the greatest scientific minds ever.
That's right, we're talking about Galileo Galilei. And he was grappling with this exact same puzzle, not on a train, but on a ship, sailing smoothly across the water.
And his experiment was just genius in its simplicity. He noticed that if he was below deck on a smoothly moving ship and dropped a ball, it fell straight down at his feet, exactly like it did when the ship was tied up at the dock. Why? Because he, the ball, and the ship were all moving together, sharing the same frame of reference. This led him to an incredible insight. If you're moving at a constant speed, there's no experiment you can do in a closed room to even prove you're moving. It's all relative. And this wasn't just some fun little brain teaser for him. This was a cosmic mic drop. He used this exact logic to argue that the Earth could be flying through space, orbiting the sun, and we wouldn't feel a thing, because we're all moving right along with it. It was a radical idea that completely upended our understanding of the universe.
So, now let's take Galileo's big idea and crank it up to 11. Because when you follow it to its logical conclusion, it gets pretty mind-bending. It turns out that the idea of being still is really just an illusion.
Okay, think about driving at, say, 100 kilometers an hour. Feels pretty fast, right? Well, that is nothing. Right now, just by standing on the surface of our planet, you are spinning through space at about 1,700 kilometers per hour. And the entire Earth, it's orbiting the sun at a staggering 107,000 kilometers per hour. But wait, we're not done. Our whole solar system is hurtling around the center of the Milky Way galaxy. And our galaxy itself is blazing a trail through the cosmos. When you add it all up, we are moving through the universe at roughly 230 kilometers per second. That's an insane 828,000 kilometers per hour. So, what's the point of all this? Well, whether you are sitting perfectly still on your couch or you're in a jet plane, your actual absolute speed through the universe is almost identical, and it is unbelievably fast. The speed of the plane is just a tiny, tiny drop in the cosmic bucket.
Which leads us to a really fundamental question. If absolutely everything, you, me, our planet, our galaxy, is constantly in motion at these incredible speeds, what does it even mean to be standing still? The concept only works if we all agree on a reference point. Otherwise, it's meaningless.
So, I'm going to leave you with this one last thought. Right now, as you're watching this, are you really sitting still? Or are you hurtling through the endless dark of space at hundreds of thousands of kilometers an hour? Turns out, it all just depends on your point of view.